Yeah.
So does it? How about as the battery ages, things change, right?
Yeah.
So how does that get handled?
Yeah, so this is the state of health parameter that everyone knows that it tracks the age, right?
Okay.
So this state of health parameter tells you the degradation of your battery. You also provide this in every individual cell, which I think that nobody is doing this, but as I told you, it's very important because you can know how your battery design is good or is bad, or if you have to redesign it, right?
Okay.
So we use also the equivalent series resistance for helping the state of charge being more accurate, right?
Okay, sure.
Yeah, we use these both because both of them vary, like in time and in temperature, of course.
Right.
So yes, this is cell state of health. Basically, what it's trying to say is the degradation in capacity of your battery from the beginning.
Okay.
Right. So
is that like 100% when it's new, and then it's a percentage of
80, for example.
total capacity?
Yeah.
Okay, that's state of health.
Yeah.
Okay. Okay. Yeah. And as you were talking about, the state of health changes over time.
Yeah.
And then also with temperature, there's changes too.
Yeah. The battery, what like we understand and what we know, and that's why we are like developing this complex mathematical cell model is the battery changes. Like if you change the current, the state of the battery changes. If you change the temperature, it changes as well, right? If you are moving through the voltage, like you are in a very, very different state in like depending on the temperature, the current, and the voltage, right? So we model all the battery in all these, like in all the ranges possible. So with only one mathematical model and using our algorithm, you can do whatever application you want that it's going to be accurate, right? Other people maybe only characterize the cells for one application or for one temperature.
Right.
But if you don't use your system for in this current profile or in this temperature, it's not going to be accurate because the battery changes a lot. Like through temperature, for example, is like changes way too much.
So like let's say a simple implementation, someone does a characterization, they might just do like one profile curve at a certain temperature.
Yeah.
So maybe one temperature, and it's a new battery, and they do the profile so they get one curve, and then they base the whole future measurements on kind of an ideal state.
Yeah.
And so
when you took, like when you, for example, if you do it at 25 degrees, right? This model, but maybe if you are riding an e-bike and it's in the winter, like you are at 10 degrees, right?
Or
0 degrees.
In the summer, same bike, but different times. Yeah.
And maybe, okay, if you are at 25 degrees, maybe the state of charge is really good, but if you are at 0 degrees, I can assure you that it's not going to be that accurate.
Right.
It's not going to be that accurate.
Right, and so like let's say a less sophisticated fuel gauge would have the one profile, they'd have to optimize it somehow to deal with the temperature. But is it, I'm just thinking through the model we have. So we're characterizing to deal with age, temperature, what other concepts that?
Using this, using the model, in our algorithm, we can also calculate the runtime, like the time to full, the time to empty. We also can know the fast charge time, right? And all this, like the available maximum power. We also have this is also really important. From our characterization, we also extract a thermal model of the battery that it's implemented in our algorithm. So we can predict at what temperature your battery pack is going to reach the end.
Okay.
Right?
Okay.
So why is that? Because the battery like the internal states of the battery changes a lot with temperature. So, but if you start at 0 degrees, because the environment is at 0 degrees, as you start discharging or charging, your battery is going to self-heat itself, right? So the end point maybe is 20 degrees.
Right.
Yep. But if you don't have this thermal model that can predict what's going to be the end point, you may calculate the shock for 0 degrees.
Right.
But you are really at 20 degrees.
Right.
So you are going to be a really huge error because the state of charge at 20 degrees is very different than at 0 degrees. So with this thermal model, we can more accurate deliver a good state of charge. And this is something that we also extract from the characterization.